Now, I want to show you a mechanism which is called catalytic mechanism in the literature. Okay. So, this is little different from what we have seen so far. So, what we have seen so far, very simple equation, where directly something goes into solution, or it can be A becoming B plus electron, where of course, these are charged species with A and B differ by one charge. It is similar to this, we have seen this. We have seen a case where it goes through one intermediate M plus solution, M2 plus solution, does not matter. If you have M2 plus solution, it is going to be with electron. So, this is another mechanism. Third mechanism is what we just saw, where you have two intermediate species. Okay. One intermediate species, you get one equation, you can just rearrange it and go. Two intermediate species, you get two equations, two unknowns. You realize that it has to be solved using matrix formulation or something equivalent to that, but it involves n number of linear equations in d theta by dE. You can solve them and get the answer. Once you know how to do it for 2, you can do it for any number. It just becomes more lengthy, but it is not more difficult in terms of understanding and approaching the problem. This is little different. Okay. In addition to this, we also saw one mechanism which we denoted as this, where you have a reaction, reversible, irreversible. We have taken an irreversible reaction in that example because it was little easier, but even this reversible you can handle it. In addition, so we have one reaction happening here, P going to Q, we also have A minus adsorbing on top. So, this becomes reaction in parallel. We have seen that, and in that case we saw that current can increase and decrease, and therefore, it can give rise to impedance like this if you are taking in this DC potential. Okay. Now, I want to show you a mechanism called catalytic mechanism, where you can get similar negative resistance values. But first I want to take a mechanism which is not really going to give you a good steady state current, but this is easy to explain what happens in the physical system, and then we will use a slight variant of this. So, the first reaction is metal goes into metal plus adsorb plus electron. We have seen this before. Metal loses an electron, it is an ion on the surface, it has not really come out from solution, it just loses an electron, we call it as M plus adsorb. Now, the M plus adsorb in conjunction with the vacant metal gives you an electron, it becomes M plus adsorbed, M plus solution and electron. I want to explain this in detail with picture. So, here the top level, these atoms are surface atoms, this is inside. Okay. So, this is exposed to solution on here, this is covered with insulator on the side, it is just that we are seeing it from the side, visualization it is okay, and there is an anion like chloride ion. Now, first step happens here, metal becomes metal adsorbed plus electron, one electron is lost from this location. So, this has become ion, I am denoting it by grey color. Because it is positively charged, it is likely that the anion comes closer to this. Next, notice it, this top right corner is a metal. Now, one to the left of that is the M adsorbed. When the anion comes here, the anion is negatively charged, it comes close to this and it is also somewhat close to the top right atom. Because this is negatively charged, it is easy for the electron to be taken out, it will repel the electron, it is easier for this atom to lose an electron compared to other neutral atoms, that is at least the hypothesis. Okay. So, this is not completely ionized yet, I am just marking it in a slightly different color to tell you that it is likely to lose an electron. So, this step I am splitting into two steps for our visualization. So, metal adsorbed plus A minus forms a bond, metal adsorbed A minus, it forms a bond or complex, metal atom, the neighbor here which is in proximity to the anion is likely to lose an electron. So, what happens is this loses an electron and this becomes M adsorbed. So, M adsorbed plus M in presence of anion, anion does not really come and sit on the surface and block for long enough time. We say there is one atom here, one ion here, anion comes, because it comes close to this, it repels this electron and this electron, the atom loses an electron. This cation which is already M adsorbed, that bonds with this and goes out into the solution and exposes the metal below. So, what happens is this was M adsorbed and this was metal. Now, this has become M adsorbed and this has become metal. This has become metal means this has gone out and the vacant site below is available. Okay. So, this what was originally M adsorbed, that has gone into solution. So, it is like one atom is here, another atom is here, this is ion, this anion comes, it pulls this out leveraging this and this becomes M adsorbed and this, not the original M adsorbed has not become metal, it is gone out into solution. So, if you look here, it is going to be written as M adsorbed plus M to tell you clearly this metal has become M adsorbed here. If this mechanism, the way I express it, if you use an isotope, radioactive isotope and say this atom is different, that atom is different, chemical properties are same, but I can identify which is what. Then this metal has become metal adsorbed, this metal adsorbed has gone into solution and this has given rise to a vacant metal site now. And of course, electron is taken because this has lost an electron. So, it is called as catalytic because at the end of it, it is like metal going to metal solution, net M adsorbed has not changed, the fractional surface coverage of M adsorbed has not changed. You got one M adsorbed here, one vacant site here, now it looks like it just changed, although it is not exactly same, one has gone into the solution, but number of vacant sites and number of M plus adsorbed site, they have not changed at the end of this process. So, in chemistry you would normally say catalyst, it will participate in a reaction, but at the end of it, it is not consumed. Of course, catalysts get poisoned, no, we will ignore all those things. Catalyst is something you put reactant, reaction happens, of course, it gets involved in the reaction, only then it can make it faster. But at the end of it, it is not like a reactant which gets consumed, this is comes back. Likewise, here we are not increasing or decreasing the number of sites, therefore, it is called catalytic. You can also imagine that the anion is catalyzing the reaction in terms of taking the metal into solution and pushing the electron inside this electrode. So, now you visualize this, I would like you to write the mass balance and charge balance equations for this. What is going to be the charge balance equation? I am going to call theta as the fractional surface coverage of M plus adsorbed. There is only one species here. I am taking actually a simple equation. You can have it for multiple species and you can say one of this step is catalytic step, that is all okay, but we want to take the simplest one. So, vacant metal site is going to be called as 1 minus theta, bare metal site is 1 minus theta, theta is M plus adsorbed. First step is going to give us an electron. Second step involves, it is a second order reaction. There are two species. So, if I say A going to B, it is a first order reaction as long as it is an elementary reaction. If I say A plus B going to C or whatever, it is going to be second order because you have two species involved. First one is going to be written as theta, second one is going to be written as 1 minus theta, correct. All these things, this tells the number of electrons produced. Of course, I multiply by Faraday constant, I will get . What about the rate of change of theta? Second step does not produce or consume theta, it does not produce or consume M plus adsorb. Net effect is it does not do that. First step will produce. Am I correct? Am I missing something? Okay, this is not the place to write. Now, what will be the steady state concentration of theta? 1. Basically what happens is, first step produces M-adsorbed. So, if site is vacant, it is going to become M-adsorbed, if not now, a little later. There is a particular rate at which it happens. Second step, whenever it sees a vacant site, then only the second step happens. You need a vacant site in conjunction or right next to a adsorbed site, both are necessary. So, whenever there is a vacant site, the second step will proceed. If there is no vacant site or if there is no adsorbed species, second reaction will not proceed. It needs both of them right next to each other. So, I can't have it completely bare metal, then the second step will not happen. If I have it completely covered with M-adsorbed, second step will not happen. So, in the beginning, production of M-adsorbed will always keep happening by the first reaction. It may happen at a slow rate or a fast rate depending on the value k, but anything that is vacant will get converted to adsorbed species. Anything that is adsorbed, net it will not get converted, it will not be consumed. That means, sooner or later the entire surface will get covered with adsorbed species and you will not have any further reaction. If everything is adsorbed, theta equal to 1, 1 minus theta is going to be 0. So, there is no bare metal site. So, imagine you have 100 sites, 99 of them are already adsorbed, one site is there. Because of that, the second step can still happen, but sometime or other the bare metal is going to become, via the first step, it is going to become M-adsorbed and then it will stop. So, steady state solution is theta SS equal to 1, that means current is going to be 0. So, this mechanism I use it to illustrate how the second step should be visualized and how to write the mass balance equation and charge balance equation for the second step. First step you all know, we have done many examples by now. So, steady state surface coverage and current values are not that good. This actually I should have put in animation, does not matter. So, I want to propose another variant where you will get a non-zero steady state current. So, let us say first reaction is reversible. That means, if you have M-adsorbed species, it can become bare metal by taking up an electron. For this, I would like you to write mass balance equation and the charge balance equation. Is this okay? So, we know the process by now. So, you got the mass balance equation, you got the charge balance equation and you can do the steady state theta value simple rearrangement. I would like you to get d theta by dE. This is also similar to what you had done for one adsorbed species. So, please go ahead and write the equation for d theta by dE by taking this mass balance equation and expanding it in Taylor series, truncating it. So, K1, K minus 1, K2, all of them are dependent on potential electrochemical steps. Therefore, you would write like this, there is only one theta. So, you do not have to write it as theta 1. So, you can write the expression for K 1 1 minus theta, K minus 1 theta, and on the right hand side substitute for both terms, then rearrange. It is going to take you few minutes, but you can do that, and you should get an expression that is given here, as long as I have done that correctly. See, if you get the expression correctly and give the kinetic parameters, if you write in a programming environment like MATLAB, which is what we use, or C++, any of those, within a second, as long as you give the kinetic parameter, set of frequencies, you would get the result. It is just you want to do it correctly. When you write the equations, you may have to spend some time to do this correctly. You may have to spend some time to program, but it does not take time to calculate it. Do you get d theta by dE? If you get it, let me know. Twinkle?
The final expression K2 dc won't be there, it is K minus 1 dc.
Thanks. In the mass balance equation, K2 does not come, because K1 dc 1 minus theta ss is equal to K minus 1 dc theta ss. We can write in a slightly simplified form. It is more useful when you write in paper. When you put in a program, it does not matter, it is all the same. So, I assume that if you are given enough time, whoever has not completed yet will complete it. This is a little more fun. Let us see if I have space in the next one. Whole thing within the bracket multiply by Faraday constant tells you the current. So, I would like you to expand here, leave d theta by dE as it is, because we know we can substitute from the previous page. The only thing you need to take care is theta 1 minus theta. You can either multiply that and write it as theta minus theta square and then do this, or you can just take it as theta ss plus d theta by dE AC. As long as you make sure that the EAC square and higher order terms are thrown away, it is okay. So, you have K2 theta 1 minus theta, each one of them will give you a EAC term. So, you will get up to cubic term, does not matter. You retain constants, you retain the EAC term, anything which is higher order you throw it away, neglect it, and then you will see that the terms that you get here, okay, it can be segregated as DC and AC, and you will get expression for this. it is approximately equal to you get 4 terms, out of which you retain 3. The last one last time you can split into 2. First one, of course, you know how to handle it. It is just like writing k 1 k minus 1 whatever into theta. Second one, you are going to get k 2 theta square. First I will write the steady state part. You know what you get when you take a derivative of y with respect to x, you will write it as dy by dx. If it is y square, you are going to write it as 2y dy by dx, that is all. So, if it is theta square, when I take the derivative, I would write it as 2 theta d theta by dE. That is one way of looking at it. Another way is to just expand theta as theta SS plus d theta by dE into EAC, then theta square, multiply them and then retain the constant on the EAC term and then throw away the AC square term, you are going to end up with something like this. Thing is, it is a second order reaction. Therefore, you are going to get, you are still going to get only d theta by dE. To determine the d theta by dE, you do not have to worry about this at all. To determine the current, you will have to look at this as the second order equation, and you will get an expression which is little lengthy. You have to do it with care, but you will get the expression here. First look at the IF, and after you rearrange this, you can write IF as IF DC plus IF AC, where IF AC depends on EAC, IF DC is independent of EAC, and you can rearrange and get, after some time you will be able to get. So, the first part out here, this part k 1 DC 1 minus theta SS goes away into IDC, this part goes into IDC, this goes into IDC, this goes into IDC. Whichever depends on EAC, 1, 2, 3, 4 terms here, 1, 2, 3, 4 terms here, oops. You would get d theta by dE from the first term, you will get d theta by dE from the second term, you would get actually 2 terms for d theta by dE from this expression of k 2 theta 1 minus theta. So, we will get actually 4 terms here into d theta by dE. Other things you can rearrange, you can simplify a little bit using the steady state condition. Sometimes you can get a little simpler expression, and I think I am missing, no, I am not missing it, I am just grouping them together here, it is a little different. Are you able to get it? If it needs time, let me know, but I would like you to actually do that and see, because if you face problem, better to sort it out here. As long as we assume solution resistance is negligible, as long as we assume the mass transfer is rapid, if you know how to handle the reaction given here, catalytic mechanism, if you know how to handle two adsorbed intermediates, you should be able to propose any mechanism and write the expression, impedance expression for that mechanism regardless of how complex it looks. Catalytic is a slightly tricky one. What you have seen before, two adsorbed intermediate, you can handle single adsorb, multiple adsorb. You had seen EEAR, which is basically one reaction, electrochemical reaction, electron transfer reaction occurring in parallel with adsorption reaction. Now, you can propose some reaction saying there are 5 steps, 4 intermediates or 3 intermediates, maybe one reaction is happening, catalytic reaction is happening along with the regular reaction. So, in this example we have said metal become metal adsorb, it is reversible. I can also say along with this catalytic mechanism, I have a regular reaction where metal adsorb becomes metal solution, that is another reaction mechanism. So, like that I can come up with many variants, you can come up with your own variants, all of them you would be able to write the expression for this, you would be able to tell the impedance provided kinetic parameters are given. So, in order to ensure that you can do that, I would like you to derive and make sure that you get the expressions correctly. You can rearrange it, you can substitute for d theta by dE, that is what I have done here and given you the expression. One set of kinetic parameters, okay, K1 B1, K minus 1, B minus 1, B minus 1, it will be nice if it is given in one line, but okay, K2, B2, gamma value and a reasonable double layer capacitance value gives you a current like this. What it means is, when potential is very low, forward reaction is not happening to a large level, this reaction is not happening to a large level, we are not getting electrons because K1 is small, K2 is small, current is more or less 0. When potential is very large, K1 is large, K2 is large, K minus 1 is small, no problem at all, but when it is large, most of it is metal adsorb. So, theta goes to more or less 1. It is not going to remain at 1 because some of it, when it is close to 1, some reaction will happen in the reverse direction. It is not 0, it is a small value, but theta is almost 1. Therefore, net current is almost 0. So, under steady state condition, if I go to 1 EDC, this is the value I get, I go to another higher potential, current keeps increasing. After some time, when surface coverage becomes significant, this current value keeps decreasing. So, this is similar to what you have seen for EAR, although it is a different mechanism, it involves different type of species, but this can also give rise to a curve like this. Here if I go to EDC, E subscript DC, at 0 potential I get 2 semicircles here, 0.05 slightly away from this. So, this is here, somewhere here I get a capacitance with a inductive loop, 0.25 is probably somewhere here I get a capacitance with a negative resistance. Now, just think about this, if you use electrical circuit for this, you are going to use, forget the solution resistance and double layer capacitance, this part you are going to use a resistor, capacitor. This spectrum you are going to say, okay, this is what I am going to use. This spectrum you are going to say I will use this, but I will come up with a negative value here, and you have to reconcile the same system at different potential. Why does it behave like a capacitor? Why does it behave like a negative resistor? Why does it behave like an inductor? So, that approach is not a good approach. It is not behaving like an inductor, it is not behaving like a negative resistor. It is giving you a spectrum that can be generated by a circuit with inductor, it can be generated by a circuit with capacitor, can be generated by a circuit with negative resistance. It does not mean that this reaction or this system has an inductor inside or has a negative resistance inside. It is a simple kinetic reaction, kinetic parameters and the potential are such that they give rise to spectrum like this. Physically you can tell what is happening here, what is happening here, what is happening here. Here you can say when I increase the potential, adsorbed species become more. So, current increases little bit because of that, but the second step which gives current, that is decreasing a lot. So, whenever potential is increasing, the reaction forward reaction rate constants K1 and K2 they are increasing. Physically it is meaningful. It is just that the combination works in such a way that one current increases a little, another current decreases a lot, because the theta value is also playing a role, and theta value increases, that causes the second reaction to go down. Theta into 1 minus theta, it will show a maximum. When theta is half, this particular thing is going to show a maximum. When theta is 1, it is 0, when theta is 0, it is 0. So, because of that, the net current decreases at low frequencies. Using one set of kinetic parameter, now I can generate spectra at many potentials, right. If I am using a circuit, each one I have to come up with one R value, another R value, another C value, and then slightly higher one I will have to come up with another value, and at some point this capacitance is going to become like an inductor, or it has to become a negative resistance and capacitor. I will have to come up with some explanation. If I am restricting my mind to looking only at electrical elements, I will have difficulty in explaining what is happening. If I tell this is probably coming from a kinetic and I can explain this reaction using kinetic parameter, I can use one set of kinetic parameters for all these potentials, all the spectra that I get here can be generated from one set of kinetic parameters. Another variant, it is just one example I have shown, where if you have forward reaction and the second step, that does not give you a valid steady state solution with non-zero current. If I make it reversible, I basically have to produce a metal site. This does not consume adsorbed species. The forward reaction only produces adsorbed species. I can consume it by making it reversible. I can say M become M adsorbed, and it can go into solution as a normal step. This is the first mechanism we have seen for one adsorbed intermediate. In addition, this goes via the catalytic path. That means, if I have a surface, if this is M adsorbed, it will go, this is also M adsorbed, this is bare metal can become M adsorbed by the first step here. M adsorbed can directly go into solution even in the absence of anion by this step, but if I have anion, the anion can come, and if the neighbor happens to be a vacant site, it can also go via this step. So, this is parallel step, M adsorbed going in template solution, but it regenerates an M adsorbed here by working with the bare metal site here. So, net if I just do the algebra and cancel out this, it is like M going to M solution with an electron. This also will give you a steady state solution, meaning a steady state solution where theta is not 1, where current is not 0 for reasonable values. If you go to extreme value, of course, current will go towards 0, but not at, it will not be settling at 0. So, this again depending on the kinetic parameter value, you will get current like this, you will get negative resistance. So, it is possible to explain negative resistance by different types of mechanism. You will have to have some idea about the system. You will have to say that okay, there is one reaction happening, species P becoming species Q. In addition, I have, so this P becoming Q is the EAR reaction, where we say P and Q are in solution. In addition, if I put this chemical A minus, then I am seeing this pattern. That is one. Second, we are not adding any chemicals here specifically to adsorb. It is just that A minus happens to be in solution and you see this behavior because of catalytic reaction. If you do not have A minus, you do not have this. So, you will have to come up with some idea, you have to come up with some proposal for a mechanism and then see if that mechanism can explain the results here. So, we will stop here today.